In this video, we'll go over how to solve differential equations, particularly by using the Laplace transforms. Here's a quick review on the nature of differential equations. An algebraic equation like y plus 3 equal to 0 is fairly simple to solve. Its solution is a number, y equal to minus 3. If you plug that number in, the left hand and the right hand side both become equal to 0. A differential equation like y dot plus 3y equal to 1 is more complicated to solve, and its solution is a function of time. We can represent this as a block. The input function ut, which currently is a constant function equal to 1, goes in and produces the output function y of t, which is a solution as shown. Note, it has a particular part 1 over 3, which is a solution all by itself, and a homogeneous part which is governed by the pole minus 3. The coefficient c will be determined by initial. In general, for an nth order differential equation as shown, the solution will have a homogeneous part with n exponential terms who have poles as exponents, and a particular part ft. This solution is only valid for an LTI system, i.e. a linear differential equation with constant coefficients. By understanding the nature of this function, we can plot the rough graph of the solution very easily. It's a three-step process. First, find the poles. Then find and plot the particular solution f of t, which, by the way, usually looks like the input function for simple cases, but it is right-shifted, i.e. time delayed. Finally, the solution graph starts from the initial condition and exponentially approaches the particular solution, if all the poles are negative. If any one pole is positive, the solution graph will go to plus or minus infinity. Also, if the poles are complex numbers, there will be oscillations in the graph, and the frequency of oscillations is the very imaginary part of the pole. But there is another way to solve a differential equation. We can use Laplace transforms. We shall see that the Laplace transform converts derivatives into multiplication and integration into division. Hence, a linear time invariant differential equation gets converted into a linear algebraic equation, which is much easier to solve. So what are these Laplace transforms? Well, simply speaking, they convert one function into another function. If you give to Mr. Laplace a function of time, he will return back to you a function of s, which is y of s. And this new function in a new variable s is often more convenient. It has more convenient properties, as we shall see. We often write the Laplace version of a function by corresponding capital letter. So yt becomes capital Y of s. Here's how Laplace does it. This integral as shown is the definition of a Laplace transform. Your function of time yt is multiplied by e to the power minus st, and this product is integrated from origin to infinity. Actually, from a slightly negative number, i.e. from slightly left of the origin to infinity. We call it 0 minus. This math particularity is to include the effect of impulse functions, among other things. Impulse functions start going to 0 slightly before origin and then come back to 0 slightly after origin. This math particularity of 0 minus also helps with some of the properties of the Laplace transforms that we shall see shortly. After integrating and plugging in the limits, the time variable is gone, only the parameter s remains, hence you get a function of s. This function of s is a Laplace transform of the original function of time. Here are some common examples of Laplace transforms that you need to remember. This table shows functions in time domain and their corresponding functions in the s domain. Laplace of an impulse function is 1. Laplace of the unit step function is 1 over s. Unit step function is 0 for all negative numbers and then jumps to 1 at origin and stays there for all positive numbers. Laplace of the ramp function is 1 over s square. Ramp function is 0 for all negative numbers and then becomes a line of slope 45 degrees for positive numbers. We can write ramp function as a simple linear function ft equal to t multiplied by a unit step function. Multiplying by unit step function basically kills that function for negative values and makes it 0 for all negative numbers. Similarly, we have Laplace of general power function t to the power n, Laplace of and also Laplace of decaying exponential is 1 over s plus a, and we shall use that shortly. Laplace of sine and cosines have the form of a polynomial divided by a quadratic polynomial. Okay, note one thing. Why are we multiplying all these nice time functions by unit function? I.e., why are we basically making these nice functions 0 for the negative values? It's not as if Laplace transforms care about the negative values, because look at the definition of Laplace. The integration is only for the positive values. It doesn't care about the function at the negative values. But you see, it actually does. Note, the integration starts from 0 minus, which is a small negative number, and having functions which start with 0 value at 0 minus simplifies some of the Laplace transform properties. Anyway, the most important property which we shall use is that Laplace converts derivatives into multiplication. If you take a function of time, yt, its Laplace is capital Y of s. But if you take the derivative of y of t, its Laplace is s times y of s minus the value of function yd at 0 minus, which is often the initial condition. It's interesting that when you do derivative in time domain, it becomes multiplication by s in the s domain. Here is how, by the way, this is the proof. Let's try to find the Laplace of derivative y dot by using the original definition of Laplace. Alright, so here we have an integral. Then we can try integration by parts to convert the integral involving y dot into an integral involving y. After plugging in the limits, we get that the Laplace of the derivative of a function is s times the Laplace of that original function minus the function value at 0 minus. This is the most important property of Laplace transform. Here are some other interesting properties of Laplace. Laplace is a linear transform, so Laplace of linear combination of two functions is the linear combination of Laplace of individual functions. We've already seen the derivative property. Differentiation in time domain is equivalent to multiplication by s in the s domain. But we can also apply it twice to get the Laplace of the second derivative of a function. Check this one out closely. You can pause the video if you want to. An inverse of differentiation is integration. Hence, expectedly, when you integrate a function in time domain, it is equivalent to division by s in the s domain. So integration is equivalent to division by s, differentiation is equivalent to multiplication by s. Another property called frequency shift is also very useful. Multiplying by decaying exponential in time domain is equivalent to shifting the s domain function by a constant amount. It is by using this property we can prove that the Laplace of exponential e to the power minus at is 1 over s plus a. Finally, the final value theorem is another important property. It says that the final value, that is the value of a function at infinity, is same as taking the Laplace version of the function, multiplying it by s, and then setting s equal to 0. But in the end, remember that the most useful property is the derivative property. Using this property, we can convert derivative into multiplication and hence differential equation into algebraic equations. Here's how. Consider a differential equation y dot plus 3y is equal to unit step function, which is basically a constant equaling 1 for times greater than 0. Let's take the initial conditions to be 0 also. As seen before, the solution is the following function for positive times. But what if we take the Laplace of this differential equation on both sides? Laplace of y is capital Y. The Laplace of y dot, as seen before, is s times capital Y minus the initial condition, but that's 0. And Laplace of the unit step function is 1 over s. So here is how it all looks like. Note that I have also secretly used the linearity property over here. Now we have converted the differential equation into an algebraic equation. And this equation is really easy to solve. Just rearrange it to get y of s equal to 1 over s times s plus 3. So that's the solution. This is perhaps the most beautiful thing ever. We can convert a differential equation into a familiar algebraic equation and then solve it easily. Let's summarize this process. So you have a differential equation with initial conditions. You can solve it by some means to get to the solution function. Otherwise, you can take the Laplace of it and get an algebraic equation. And note, this algebraic equation only happens when you have linear time invariant systems. Then you can solve the algebraic equation fairly easily. But the problem is that the solution you get, capital Y of S, is in the S domain. So then we can take the inverse Laplace transform to convert the S domain function into the time domain function. And that's how you find solution using the Laplace transforms. And this is quite cool. As a last note, the inverse Laplace here was done using partial fractions. 1 over s times s plus 3 is converted by algebra to be 1 over 3 times 1 over s minus 1 over 3 times 1 over s plus 3. Since the Laplace of a unit step is 1 over s, the Laplace inverse of 1 over 3s is 1 over 3 times the unit step, i.e. 1 over 3 for time t greater than 0. Since the Laplace of e to the power minus 3t is 1 over s plus 3 as seen before, the Laplace inverse of 1 over 3 times s plus 3 is 1 over 3 times e to the power minus 3t. This is how you use partial fractions to find the Laplace inverse.